In Lesson 55, what we're going to be looking at is graphing or learning to solve systems of linear equations by graphing. So this is Lesson 55, learning to solve systems of linear equations by graphing. Our objective here tells us what we're doing, but what do we have to know in order to do this? Well, that's one of the skills, but just look at this sentence. Learn to solve systems of linear equations by graphing. We know what graphing is. What do we need to know? What do we need to define from this objective? No, we know what that is already. Systems of linear equations. We need to know what this is. Systems of linear equations. We need to know what that means. Okay? So that's the first thing that we're going to define in our lesson today. Talk about what it means. And if we're going to learn how to solve it, we need to learn what a solution looks like. We just did in our Bell work, we just saw that the solution to a linear equation is an ordered pair. So we know if we have a linear equation, y equals mx plus b, or ax plus by equals c, or y minus y1 equals m times x minus x1. That's the three forms of a linear equation that we've worked with so far. If we have any of those things, a solution to one of those things is an ordered pair that's on the line. All right. If it's on the graph, that means algebraically, if you plug it in, you get a true statement. Okay. So we know what a solution to that looks like, but we need to define what a system of linear equations is and what a solution is. All right. So let's jump into some important concepts here, and they're all here. It's not animated, so you'll see them at once. But let's just focus on the first things first, okay? A system of linear equations, this definition, is two or more equations whose graph is a line. It's two or more linear equations, okay? That's what a system of equations is. Two or more linear equations. Okay. The second point here gives us some very important information. If we're going to solve it, we need to know what we're looking for. We need to know what the solution is. The solution to a system of linear equations will be a point or points where the lines intersect. So we're looking for the intersection point of the two or more linear equations. Now, in this class, we're only going to be doing two equation systems. We're not going to have multi-equation systems. Just two equations and two variables. Because you could talk about the solution to a linear equation in three variables, three-dimensional graph. And you'll do that in Algebra 2, and in college algebra you'll do that. But in Algebra 1, we're just going to be focusing on the 2 by 2, or two equations, two variables. All right? So let's finish this. Don't worry about the third and fourth bullet points at this point. Let's discuss some of the things, the details in this. The solution to a system of linear equations, two or more equations, is the point or points of intersection of the two lines, the point where the lines intersect, assuming the lines aren't what? Parallel, because if the two lines are parallel, then they will not intersect, right? Parallel lines do not intersect, so if a system of equation involves parallel lines, that's our special case of no solutions. How do you identify parallel lines? They have the same slope. Okay? Good, so same slopes. And lines that are concurrent, now this says point or points. How could two lines have more than one point in common? How do they intersect twice? Can they intersect just twice? They can't, right? In order for two lines to have 2 points in common, they have to have all points in common. So this is an all solutions kind of thing, but lines that are concurrent share all points in common. But we don't say all real numbers because the solutions aren't numbers. The solutions are points. So we'll say infinitely many points or infinitely many solutions. Okay, let's just say infinitely many solutions or points. Those would be two lines that are exactly the same. You want to see an example of what that might look like? Here's an example of what that might look like using the bell work problem that we just started with. You might be given a solution, or you might be given an equation, a system of equations like this. 2x plus 3y equals 6. And the second equation is y equals negative 2/3 x plus 2. Now, we know very well, because of the bell work, that that system of equations is the same two lines. One's in standard form and one is in slope-intercept form. If you graph those two lines, you're going to see that the two lines are the same and they have all points in common. So the solution to this system of equations isn't a single point, but it's infinitely many points. All right? They're the same line. Infinitely many points in common. So, all right? Y'all good with that? So that's just a scenario where the two lines may be the exact same lines, and we have to deal with it that way. All right? Example 1. This says, tell whether the ordered pair is a solution of the given system. Now, in order for it to be a solution of the given system, what does that mean?
They can't be parallel.
They can't be parallel, but this point has to do what?
Oh, it has to fit.
It has to fit this equation, and it has to fit that equation, right? So we just have to test and see if that point is on both of those lines. In other words, is this point going to make both equations true? Is 3 times 1 plus 2 times 2 equal to 7? Yes. Is 2 equal to 7 minus 3 times... No, I did that wrong, see? X is 1. Is 1 equal to 7 minus 3 times 2? Yes. So we would say 1, 2 is a solution. To the what? To the system, because it makes both equations true. So what does that tell us? What is 1, 2? What's the significance of 1, 2 as it relates to these two lines? What is this? It's a solution, but it means it's where these two lines do what? Intersect. Those two lines cross at that point. All right? The solution to a system of equations is the point of intersection where the two lines meet. And that's redundant, I understand that, but it's the point of intersection of the two lines. Okay? All right. What about this one? Is 2, 3 the intersection of those two lines? And what I'm asking is 2, 3 the point of intersection of these two things? Let's just plug things in, right? It's 3 times 2 plus 2 times 3 equal to 12. Yeah, that one's good. Is 2 equal to 7 minus 3 times 3?
No, it's negative 2.
7 minus 9 is negative 2, and this is not true, which means 2, 3 is not a solution to what? To the system. It's a solution to this linear equation, but in order to be a solution to the system, it has to be the point where the two lines intersect each other. Okay? I want you to understand what we're doing graphically, even though we haven't graphed any of those. We're going to start doing that right here. Solve this system by graphing and then check your solution. Okay? We want to solve this by graphing and then check our solution. So grab a piece of graph paper that I gave you just a moment ago. And we're going to graph y equals x plus 3 and y equals 2x plus 1. And we're going to find the solution graphically. Now, let me ask you this question. Before we ever start, is there going to be a solution? I'm going to use colors here because I can. Is there going to be a solution? How could we tell if there's not going to be a solution? The lines are parallel, which means they would have the same slope. Parallel lines don't intersect. All other lines do. Are these lines parallel? So there is going to be a solution because lines that aren't parallel are going to intersect, and that intersection is the solution we're looking for. So let's sketch our graphs. Y equals x plus 3 has a y-intercept of 3 and a slope of 1. Now, y'all don't work that far ahead of me because I'm going to show you something that's going to help you. You can use a straight edge to draw the lines, but rise over run 1, slope of 1 is just going to go up 1, right 1, right? And you don't really even have to connect the dots on these. Okay, let me show you what I mean by that. Y equals 2x plus 1, what does it do? Y-intercept of 1, rises 2 and runs 1. Rises 2 and runs 1. Right there, I have stumbled upon my intersection point. Okay? Now, if we sketch the graphs of the lines, that's fine. We can do that and show the intersection point, but this intersection is going to be the same regardless of whether I graph the lines or not. I can just do the rise and run of the points and find the point of intersection. So the point of intersection we think is 2, 5. X is 2, Y is 5. Now we're going to check that. Always check it, and you'll see in just a minute why it's very important to check it. And it's always important to go back to the original equations and check it. We didn't change these equations, but if you do change an equation, put it in slope-intercept form, and you make a mistake, you change the intersection point. So your answer would check in your slope-intercept forms, but not in your other forms. So it's always important to go back to the original equation. Is 5, 2 a solution to this equation? System of equations. Is 5 equal to 2 plus 3 in this equation? It is, right? Is 5 equal to 2 times 2 plus 1? It is a solution to both, and so it works. All right? So that's what we're doing today. Solving by graphing. Okay? Now, can you see any limitations to this right off the bat? If the numbers are really large, you're going to have one in your homework that's got like a y-intercept of 15. Even 15, that's not a huge number. It's not fun to graph, though, is it? So you may want to scale your intersection points there, or do something creative with the graph on that one. And that's going to be true. The big number ones are going to be a little bit easier to work with the graphing calculator, which we'll look at tomorrow. If you have your graphing calculators with you tomorrow. And then we can, I'm going to show you the steps on how to do this with the graphing calculator. It's kind of no sweat. All right, let's look at the next example. Maybe we can come up with a limitation on this one. What's the first step if we want to take 3x plus y equals 9, x plus 2y equals 8, and solve by graphing? Put it in slope-intercept form. That's just the way that we're most used to graphing, right? So I'm going to save us a little time because I know you guys have this skill down pat. The first equation would be y equals negative 3x plus 9. The second equation is going to be y equals negative 1/2 x, negative x over 2, which is negative 1/2 x plus 4. Right? Any issues with that? Okay, let's go to our graph paper. Now here we got positive 9 as a intercept point, which is pretty high. All right, so slope of negative 3, which means I want to go down 3 and right 1. And again, just plot your points for now. And then y equals negative 1/2 x plus 4. It's going to have a y-intercept of 4. And what is it going to do? Down 1 and right 2. So down 1 and right 2, that gets me right to the intersection point. Yes? So those 2 points are in common. So this line is going to be there. This line is going to be here. And the intersection point, it looks like, is 2, 3. Now, this is an extremely important thing, what I'm saying. You have to go back to your original equation, because if you made a mistake putting your lines into y-intercept form, slope-intercept form, this solution would check out in your mistake, because that's the lines you craft. So you always go back to your original equation to make sure you didn't make a mistake either graphing it or solving for y. So if we go back to our original equation and we want to see if 2, 3 is a solution. Is 2, 3 a solution to this system of equations? So we'll do 3 times 2 plus 3 equals 9. Is that true? It's true, isn't it? And then 2 plus 2 times 3, is that equal to 8? It is, and so we're going to keep that answer. It just tells us we didn't make any mistakes solving for y or graphing our lines. Okay, one more. (2x plus y equals negative 2). Y equals negative 3x minus 5. Now, we know we're solving a system of equations here because the directions tell us it's a system. Okay? Sometimes you may have in other algebra textbooks, you might just see solve, and then you'll see this little bracket thing there that ties the 2 equations together. That tells you we want a solution for both of those things. All right? But our textbook's going to always kind of tell you it's a system that we're working with, or it's going to tell you to solve it. So again, first thing we have to do is put each line into slope-intercept form. The first one's going to be y equals negative 2x minus 2. The second equation is y equals negative 3x minus 5. All right. All right, so let's do this first one in green. Negative 2x minus 2 has a y-intercept of negative 2. Down 2 and right 1. Slope of negative 2 is down 2 and right 1. Or we could go up 2 and left 1. The other one is negative 3x minus 5. Oh, let me do that one in red. Now, this one is not going to be very friendly to go down 3 and right 1. So I want to go up 3 and left 1. Up 3 and left 1. Up 3 and left 1. All right, now it looks like if I graph this one more point, up 2 and left 1 for the green, and I'm going to have my intersection point right there. Oopsie. Let me use a solid line for that. So there's my red line. And my green line look like this. And it looks like our intersection point is at, oopsie, that's not right. I don't know why I keep saying oopsie. It's not really in my normal vocab. All right, so it looks like our intersection point is right there, which is -3, 4. So you see how you may have to count up till your lines actually cross? Mm-hmm. And the limitation of this is what happens if your lines don't cross at a grid mark?
You gotta figure that out.
We're going to have to switch to an algebraic method or use our calculators. The calculator will tell you the fractional answer. All right? So if you go back and check that, you'll see that it works. Now, your homework is this, but it is due on Friday.
Really? That's Wednesday. That's great.
Now, you will have homework tomorrow, so it'll double up at some point, but you'll have time in a study hall or something tomorrow to take care of that. All right?
I'll be right now.